of this particular session. At the outset, I thank our Professor Koteswar Rao Garu for accepting our invitation to be as the resource person for delivering this talk uh, in connection with this FDP on advanced materials and manufacturing process. Advanced materials in connection with nanotechnology, I think. Yeah. Welcome to one and all. This program consists of 2 weeks. First week is of online and the second week is of offline. So first week online session every day starts from 7 and ends by 9:30. So 7 to 9:30. 7 to 7:50 will be the talk, and there will be a break for 10 minutes, followed by again talk for 50 minutes, and there will be a break for 10 minutes again, and there will be 30 minutes interaction with the expert. Participants can interact with the experts and they can get clarification for their doubts. Right. So such sessions will be there for 6 days, 6 sessions. In addition to which, on 17th, offline week is going to commence, and in the offline week there are 8 sessions. Each session will be of the same duration of about 2.5 hours, and there will be one industrial visit as well. So I request all the participants to make utilize of this workshop, because all the resource persons are very eminent personalities from IITs, central universities, reputed R&D labs, and state universities. So it's a wonderful opportunity for all the participants to get acquainted with the advancements in nanotechnology. So once again, I welcome everyone. So now I request our co-coordinator, Dr. Srinivas Prasad, to give a brief introduction about our resource person, Professor Koteswar Rao Garu.
Yes, sir, sure. Professor Koteswar Rao Garu is a professor in University of Hyderabad. He had his academic training in metallurgical and materials engineering and obtained his PhD from North Carolina State University, Raleigh, USA in the year 2006. He did his MTech and BTech degrees from IIT Kharagpur, India in the year 2002 and in JIT Hyderabad in the year 2000 respectively. Subsequently, he did his postdoctoral work in the University of Michigan, Ann Arbor 2007 and University of Southern California in the year 2008 at Los Angeles, USA. He has been with the School of Engineering Sciences and Technology of University of Hyderabad from 2009 onwards and is working as professor in University of Hyderabad. His research interests include nanomechanics, high entropy materials, friction steel welding processing, additive manufacturing, advanced high-strength steels and superalloys, etc. He has guided 12 PhDs and 30 MTech students so far at University of Hyderabad and currently having 7 PhD students under his supervision. He had published around 65 papers in reputed international journals and referred conference proceedings. His academic and research efforts were recognized by several national and international distinctions such as Fellow of Telangana Academy of Sciences in the year 2018, Weldwell Specialty Award of Indian Institute of Welding in the year 2018, Chancellor Award of University of Hyderabad in the year 2015. He is a life member of Indian Institute of Welding, Indian Institute of Metals, Material Research Society of India, Electron Microscope Society of India, and Plasma Science Society of India. He is also serving as one of the editors of the Transactions of Indian National Academy of Engineering, Springer Nature. So I request you to kindly extend your expertise in this area of nanotechnology and enlighten our participants. Thank you very much, sir, for your kind presence. I request Koteswar Garu to extend his expertise.
Yeah. Thank you, Professor Swaminathan Garu and Dr. Srinivas Prasad Garu for the kind introduction. It's very generous. And good evening to you all. I hope you all can hear me. Is it?
Yes,
can
sir.
you hear me?
Yes, sir.
Yes, sir.
Yeah. I'm worried about these online lecturing because you just log in and vanish from there. So I don't want that to happen. So even while I present, if if you have any doubts or concerns, I want you guys to stop my presentation. This is what I want. Let us make it more interactive.
Sure, sir. Our participants will definitely try to interact whenever there is any kind of misunderstanding that they should have.
Can you see my screen now?
Yes, sir. It is visible.
Yeah.
Yes, sir, it is visible.
Thank you. Thank you. So I work at University of Hyderabad in the School of Engineering, Sciences and Technology. We have 3 programs. One is Materials Engineering, other is Nanoscience and Technology, and the other one is Manufacturing Science and Engineering. We offer only MTech and PhDs here. We don't have any undergrad program. And our programs are highly research-centric. Each and every program, whether it be MTech or any other program, are highly research-intensive. And then, can you see my screen? I see there is something happening here. Are you able to see my screen?
No, sir.
Now? Are you able to see my presentation?
No, sir.
No, sir.
Can you see my screen now?
Yes, sir. Yes, sir.
Yeah.
Yes, sir, it's visible right now.
Yeah. So our research efforts are, the full details of our research efforts are given in this web page, and you can also reach me in connection to, with respect to this FDP or subsequently using this email address here. So as far as the, today's FDP is concerned, I will be talking about the mechanical response of multi-phase nanostructured conventional and high entropy alloys. So in this FTP or any other FTP, wherever I was invited as a resource person, what I actually do is that I consider our own research and explain the fundamentals thereof, so that the faculty who are participating in these programs will also get a first-hand information on what sort of research we are doing and so on, so that you can take back that experience to your respective academic units and then start developing your research culture. That's what I intend, and I request you all to develop the research culture back in your own academic institutions to make use of this experience. And I'll be talking about, as I said, the wide variety of nanostructured materials that we develop in our lab, and then we test them for the mechanical response. In other words, we evaluate their mechanical properties using different techniques, and then after characterizing the microstructure in detail up to atomic scale, and then we bring out correlations between the microstructure that we have seen versus the mechanical properties that we have realized. See, the reason why we want to do all these things is that I'm sure all of you might have heard something called characteristic length scale. Here, the characteristic length scale means the microstructural parameter that you are considering. For example, it can be a grain size, it can be a particle size, it can be a second phase size. And based on those things, if you can have the average dimension of this characteristic length scale as less than 100 nanometers in at least one dimension compared to 3 dimensions, then you can call it as a nanostructured material. In other words, when you work with different polycrystalline materials which are of structural engineering importance, be it aluminum alloys, copper alloys, steels, or nickel-based superalloys, or magnesium alloys, and so on, the grain size plays a major role in dictating their mechanical behavior. As a result, if you can control the grain size to less than 100 nanometers, then you can call it as a nanostructured material or nanocrystalline material. And likewise, we want to make reasonably larger samples so that the mechanical properties can be evaluated in a more meaningful fashion. And while doing so, actually your FDP title also contains manufacturing, and that's something that we all should pay a major attention to. scientifically or theoretically sitting in the laboratory, either with the laboratory scale experimentation or using wide variety of simulation tools, you can virtually make any type of material as a nanometer, nanostructured material. But when you want to make larger components of structural engineering importance out of these nanomaterials, it's really an uphill task to make those larger components without losing the nanostructure that you have developed. Because the interesting properties, be it mechanical or physical or optical or magnetic, whatever you call them as, all those interesting properties are originating from the nanostructure, which is the characteristic length scale here. And making larger materials out of these smaller entities without losing that nanostructure is definitely a challenging task. And if you can overcome that, yes, you are the man. So we wanted to make the reasonably bulk components without losing the nanostructure, and then we also want to put some kind of dispersides in them, which are also of less than 100 nanometer size, and try to understand what sort of mechanics will these materials would display under the application of external load or stress. And also, when you diminish the length scale, for example, from 100 nanometers to go to close to 10 nanometers of the diameter of the grain that you are talking about. So when you have 10 nanometer grains, you can virtually, you can in principle estimate how many number of atoms are sitting in that grain. The reason is that the interatomic distance, in other words, your lattice constant, is about 3 to 5 angstroms for most of the crystalline materials. Considering that as the distance between two neighboring atoms in a crude approximation, you can estimate how many number of atoms can be present in 10 nanometer grain size. So when you have slowly small number of atoms, then the presence of lattice defects becomes extremely difficult. Again, here I need to give some information about the lattice defects. I'm sure most of you have heard about the lattice defects such as point defects, which are vacancies and impurities, and also the line defects, which are called as dislocations, and then surface defects for two-dimensional defects, which are grain boundaries, surfaces, interfaces, and so on, and the three-dimensional defects, which are intrusions and then impurities. For example, crystalline materials exhibit three-dimensional periodic structure at atomic scale, whereas amorphous materials don't display any sort of periodicity or the symmetric arrangement of atoms in 3 dimensions. And there is something in between, which are called as quasi-crystalline materials, which partly exhibit some kind of periodicity. But anyway, the science of quasi-crystalline materials is entirely different. Let's not touch this in this class because of the paucity of the time. So when you have such a small number of atoms, for example, vacancy is defined as missing atom from its regular position. Whereas if you can keep a foreign atom into the original lattice, you call it as impurity. And this is fairly simple. But again, if you can make sure that a row of atoms get missed, then you call it as a dislocation. In other words, if you can have an additional row of atoms, you also call it as a dislocation. So the atomic, the atom, which is zero-dimensional in nature, when you have a group of atoms are missing, it becomes a line. That's why you call it as a line defects. And when you have planes missing, see, all these crystalline materials will have a stacking sequence. Like if it is FCC, you will have ABC kind of stacking. ABA is one plane, B is another plane, C is a different plane. Likewise, in 2 dimensions, like hexagonal close spectrum materials will have a stacking sequence like AB, and so on. A is one plane, B is a different plane compared to A. So when you have a regular sequence like this, you have no issues. But the moment you bring an additional plane into this sequence, or if you remove the existing plane from the original sequence, then you create defects called stacking faults. And these stacking faults also would help you in making mechanical response viable. And the third part is the porosity. Pores are the inclusions. And these pores definitely we don't want unless and until you are making porous materials intentionally, or if you are making foams so that they are some kind of application oriented, then your pores are of importance. Otherwise, we don't want pores in any structural material. And then if you have inclusions, these inclusions sometimes are wanted and sometimes unwanted. These inclusions will help you in raising the strength of the material by helping you in getting more amount of strain hardening under the application of stress. Sometimes they act as stress risers and they are not good based on your application. So your application decides whether you want inclusion or not. So all these lattice defects are important for you to realize the mechanical response of a given material. And although we are calling them as lattice defects, they are not really defects for us. They really help you in changing the shape of a given material. And then there is something called strain rate sensitivity. A given flow stress or a given yield stress of a material gets influenced by the load that you apply, strain that you apply, temperature that you apply, plus the rate at which you apply a load or strain rate is also important. So based on the strain rate variation, when you understand the mechanical response of a given material, then that also helps you when whether you can get a reasonably strong material coupled with acceptable levels of ductility. These strength and ductility are mutually exclusive properties conventionally. For example, if you make a very strong material, it's not ductile enough to make it into sheets, plates, and so on. Whereas if you make a very ductile material, you cannot make it strong. One you get at the expense of the other. But getting really stronger material coupled with the really high levels of ductility is still a challenge for the engineers to overcome. And while doing so, we evaluate two critical parameters called strain rate sensitivity and the activation volume. Strain rate sensitivity is something that you see change in the flow stress of a given material at a given temperature with the variation of strain rate. Sometimes when you increase the strain rate, you will have the increment in the flow stress, in which case you will get the positive strain rate sensitivity so that your material is reasonably ductile. In other words, in other cases, when you increase the strain rate, your strength will come down. That shows the negative strain rate sensitivity, and you don't want that type of materials for any kind of application because there's some kind of plastic instability. You need to avoid that kind of negative strain rate sensitivity. And some materials are not at all strain rate sensitive, irrespective of whether you increase the strain rate or decrease the strain rate, nothing will happen. And the other parameter is the activation volume. As I mentioned before, these lattice defects control the mechanics of plasticity. But to understand what sort of defects have participated in a given plastic deformation event, you need to evaluate some parameter called activation volume. So if the activation volume is reasonably high, then dislocations are the chief controls of plastic deformation, in which case your material microstructure is like the grain size of tens of microns. Whereas if you bring it down less than 100 nanometers, then your activation volume also comes down because grain boundaries and other lattice defects play a role in dictating the mechanics of plasticity. And there are two different scientists with name E.O. Hall and N.J. Petch. And these people, while working with lithium fluoride crystals way back in 1954 and 1955 time, they found that when you vary the grain size of the lithium fluoride crystals, they have seen some change in the flow stress or yield stress that they have seen. And when they tried to fit the data of yield strength on y-axis and the grain size on x-axis, they found that the yield stress will have 1 by root d type of dependence. And subsequently, several scientists or academicians have also realized this type of dependence in various other materials as well. So to respect the initial observers of this phenomenon, the whole effect, the whole scientific part of this grain size dependence or the flow stress dependence on the grain size, it is called as the Hall-Petch effect or Hall-Petch equation, which is sigma y equal to sigma naught plus k into d power minus half. Here k is the Hall-Petch constant or locking parameter, or that the value of k will tell you whether you have whether the grain boundaries are strong enough to contribute to your strengthening or sometimes they could be weaker as well, and that gets reflected in this number K. And sigma naught is the lattice frictional stress, that is the resistance offered by your crystal material to a moving dislocation. After all, in your periodic table, when you look at different materials, whether they are BCC or FCC or HCP or any other crystal structure, you see that some are hard and some are soft. And this gets originated from the fact that the moving dislocation will have a lot of resistance in harder materials, or a moving dislocation will have relatively less resistance in softer materials. Therefore, in conventional coarse grain materials, where the grain size, the average grain size is of tens of microns, then you have dislocations which are line defects or one-dimensional defects, whatever you call them as, are the main controllers of plastic deformation. So once you understand the dislocation movement in these materials, then you have a full understanding on how to develop or rather how to design stronger and stronger as well as harder materials. And the other part here, if you see the flow stress or yield strength on y-axis and grain size raised to minus half on x-axis, you see that up to 100 nanometers we have one slope, that is K shown here, and this is the conventional materials. And with the grain size between 100 nanometers and 10 nanometers, you also see that slope is still positive. That means with the decrease in grain size, your strength further increases, but again the rate of increment is different from the rate of increment that you have seen here. And this is because the change in the deformation mechanism from here to here. Up to here, grain boundaries won't play a major role. It's all dislocations that control the plasticity. But in this, in addition to dislocations, grain boundaries also play a major role. But the whole lot of interesting stuff happens when you reach the grain size of 10 nanometers. Here, whenever I say or anybody talks about grain size, it's always the average grain size. Keep it in mind. It's always the average grain size. For any given material, when you look at the grain size, it will not be of the uniform size. There exists some kind of distribution. Therefore, you should always report the average grain size with an error bar that includes the standard deviation out of the statistics. And the moment that you reach 10 nanometer grain size, then dislocations are the grain boundaries become really unstable, and the existence of dislocations is really questionable because we cannot have a dislocation in such a small grain size. And again, when you decrease the grain size further below 10 nanometers, you see that you have a negative slope here, that is minus K. This red dotted line shows the negative slope minus K. That regime is called as the inverse Hall pitch effect. Inverse Hall pitch effect. And that is till now what I talked is about the pure elemental metals, for example, aluminum, copper, iron, tungsten, molybdenum, and all those things happen there. But the moment you bring a smaller particle within the grain, this is grain and 20 micrometer size roughly. You can also take it as 40 microns, no issues. This symbol shows the dislocation, and under the application of stress, this moving dislocation will get a lot of resistance by these precipitates, and the size of this precipitate, distribution of these precipitates, and also the spacing between two neighboring precipitates also a matter of influence in these mechanical properties. And in conventional materials where the grain size, the average grain size is about 20 micrometers or more than that, the mechanics are well understood using something called Orowan kind of dynamics. Orowan was the man who elucidated the dynamics behind this type of materials. But the moment you decrease the grain size to 20 nanometers, from 20 micrometers to 20 nanometers, so you have a change in the grain size by 3 orders of magnitude. And then you also have smaller precipitates, which are also of less than 100 nanometer size. Then the dynamics, you cannot extend the dynamics that you have seen in conventional coarse grain materials to a nanostructured material. So here the grain boundary mediated process, in other words, interface mediated process such as grain boundary sliding, grain rotation and coalescence, grain boundaries acting as sources as well as sinks for either full dislocations, partial dislocations, or stacking faults could be the governing mechanisms. So schematically, the grain boundary sliding is shown here. We have set of grains here, another set of grains here. When the application of stress is applied under shear mode, you see that the bottom one gets slide past the upper one. Likewise, grain rotation means under the application of stress, grains get rotated and eventually boundaries get erased and you see a grain growth. And these things also were observed experimentally. But most of the insights to understand these mechanisms have come from molecular dynamic simulations, because to observe these things you really need high-end tools using very high resolution TEM and also the in-situ application of stress, and that is not a trivial task to do. Of course, some people have done, but all they could do is to see the movement of dislocations only up to that point. Grain rotations and grain growth under the in-situ TEM have not been observed. It's an extremely difficult task. And then grain boundaries, when you apply stress, I'm sure most of you know that the atomic arrangement that exists within the grain versus grain boundaries is totally different. Within the grain, you have some kind of periodic arrangement of atoms in polycrystalline materials. Whereas if you look at the atomic arrangement in grain boundaries, it's totally random. Plus, the initial thought process, like 40 years ago, is like that the atomic arrangement within the grain boundaries is somewhat closer to that of the atomic structure of a gas. But subsequently, it was not agreed upon largely. But yes, it's totally random, somewhat closer to gas. So as a result, the moment you apply stress, you can emanate or you can generate a lot of lattice defects. It can be a missing row of atoms, it can be a missing plane of atoms, or it can be any other lattice defect. And here dislocations are shown. So they travel across the grain and get absorbed on the other side, because you also have a space on the other side. So on one side, grain boundaries act as sources of the generation of lattice defects. On the other side, they act as sinks for the lattice defects. And these are all observed as molecular dynamic simulations. So the take-home message from whatever I presented till now is that plastic deformation mechanisms that are responsible in coarse grain materials where the average grain size is more than 20 nanometers cannot be extrapolated to the materials where the average grain size is about less than 100 nanometers. Because the governing the plastic deformation events are totally governed by different sets of lattice defects in these two regimes. So therefore, the knowledge that we have at higher grain size cannot be extrapolated down to the nano regime, or in other words, whatever you see in nanometers cannot be extrapolated to the conventional materials. And the other important point is that whether they are loading rate sensitive or not. This is what we have done. And till now, I think about 120 elements or maybe more than that are discovered from the nature, and they are arranged in a very nice fashion in the periodic table based on their behavior and also the valence electron configuration and so on into either periods, groups, and so on. But majority of the cases where you are looking for a good engineering application, you will never take any material from the periodic table and directly use it for your application, because pure materials are not good enough for any good engineering application. It's always a mixture. You always want to mix at least 2 elements and sometimes more. For example, if you take a conventional steel, at least 10 elements are added as alloying additions based on the requirements. Likewise, the sopralloys, which are used for gas turbine applications, and they are also having more than 10 alloying additions. And these small alloying additions, although minor in proportion, they control the properties to a major extent. So therefore, it's absolutely necessary to understand the role of these elements, their nature, as well as the composition and the overall behavior. And the whole exercise for a material scientist primarily is that we want to develop better and better materials as compared to yesterday. It's a continuous pursuit, and the only way is that there are two possibilities. One is directly trying to get from the nature, which is difficult. And most of the discoveries that people have found was by accidents. You cannot say that today I'm going to work on something so that I will find or rather I will discover a new material. It will never happen. They're all came into existence by accidents. But by understanding the nature of the already existing materials, you can mix them into different proportions at different temperatures, pressures, and different volumes, and then make new materials in your laboratory and understand what sort of better properties they can offer to you. And the conventional materials, or in other words, coarse-grained materials, can be strengthened using one or more of the following sequences. These are all well-established facts. One is grain refinement, where you decrease the grain size. Other is solid solution strengthening, where you mix different atoms at atomic scale. And then strain hardening, by putting some kind of precipitates, you increase the failure strain, so that before your material actually fails, it absorbs some amount of plastic energy. And precipitation hardening, by including some kind of precipitates which are either coherent or semi-coherent with your parent material, you increase the strength to some extent. For example, the aircraft materials, majority of aluminum-based alloys are precipitation strengthened materials. And the other part is the dispersion strengthening, and these are totally new set of materials where the dispersions, you can call them as second phases or fillers or any other name, and they are not coherent to the matrix. They're totally incoherent, and this type of sequence is good for high temperature applications. As I mentioned before, this is the Hall-Pitch equation. So this grain refinement can be obtained either by heterogeneous nucleation traditionally, but it sets a limit. Beyond say 4 microns or 5 microns, heterogeneous nucleation will not be of any help to you in making fine-grained materials, in other words, nanomaterials. In order to make nanomaterials, there are other techniques that come into existence, which I'll be mentioning in a few minutes. So now we are into our nanostructured materials. These are an important class of advanced materials with characteristic length scale less than 100 nanometers. And these materials exhibit novel and often superior properties compared to the materials with coarse microstructural features. And presence of significant fraction of atoms within the interfaces. These interfaces can be grain boundaries, triple junctions, or quadruple junctions. Grain boundaries means the region where 2 grains meet. Triple junction means the region where, the common region where 3 grains meet. Quadruple junction is the region where 4 grains will meet. The probability of finding a grain boundary in a given material is more compared to the probability of finding a triple junction. And again, the probability of finding a grain boundary and triple junction is much more than the probability of finding a quadruple junction because of the probability with which these grains can come together at a small grain size. So here you see the atomic structure. The schematic A shows the atoms which are open circles, these ones here. The atoms which are arranged in a periodic fashion. Actually, this is a 2-dimensional, we have a 3-dimensional arrangement. You also have the 3rd dimension into the plane of the screen. And the amorphous material shows that you don't have any periodic arrangement, it's totally random structure. So therefore, the lattice defects that I mentioned, the vacancies, interstitials, impurities, dislocations, grain boundaries, stacking faults, inclusions, and impurities, all those things are of some meaning only in case of crystalline material, not for amorphous material. And when you look at the nanocrystalline material where the grain size is about less than 100 nanometers, you see that the white ones are the ones which occupy the grain boundaries, and the filled circles are the ones which are part of the grain. Now you see that the volume fraction of the atoms that are sitting in the grain boundaries is comparable to the volume fraction of the atoms that are sitting within the grains. Therefore, these atoms also play a critical role in dictating the plastic deformation, whereas in conventional materials, the number of atoms that sit in the grain boundaries is way less by several orders of magnitude compared to the atoms that sit within the grains. And there exist several ways to develop these nanostructured materials, and based on the sequence, how they are grouped together at atomic scale, two schemes have came into existence. One is bottom-up approach, other is top-down approach. In bottom-up approach, the processes that include are inert gas condensation, electrode deposition, physical vapor deposition, chemical vapor deposition, crystallization from amorphous precursors, plasma synthesis, and so on. So in all this bottom-up approach, you start with atoms and then build the structures atom by atom. You come from the bottom, so to the top. So that's why you call it as bottom-up approach. Whereas in top-down approach, you start with the bulk material and disintegrate the microstructure into a nanoscale, for example, grain size or any other particle size and so on. So high energy ball milling is one of the versatile techniques to make a nanometal by using top-down approach. And there exist several plastic deformation methods that include equal channel angular pressing, high pressure torsion, accumulator roll bonding, friction stir processing, repetitive corrugation and grooving. And the left ones, bottom-up approach, you really can make very small grain size and really small materials. You can also make thin films and highly pure materials, but you cannot make larger samples. Whereas using top-down approach, you can make reasonably larger samples, but the grain size limit that you can achieve has some constraints. You cannot make as small grain size as you have realized in the bottom-up approach using top-down. And further, you have impurities that come into top-down approach. So therefore, the advantages that one technique offers cannot be offered by other techniques. Therefore, I made a philosophical statement here that advantages come in some kind of disadvantages in this adoption of this process. So, again, as I said before, in addition to strength, reasonable levels of ductility is also important. I just now mentioned that around 10 nanometers, the existence of dislocations is a major problem in these materials. But again, you can also not make larger samples, which can be tested using our ASTM gauge standards and so on. See, anytime when somebody says that I'm measuring mechanical properties, the first and foremost thing that we do is the tensile test. For that, we need samples of about 20 or more than 20 centimeters in dimensions. But you cannot make these nanometers into those dimensions. So therefore, you always make some kind of sub-size samples at micron scale or at millimeter scale, and then test them and then find out some kind of relation between these properties and the conventional measured properties. And in this paper, which was published in Applied Physical Letters way back in 2005 from the lab where I did my PhD, it shows that there is some kind of dislocation activity in a copper grain whose grain size is about 20 nanometers. And also because of dislocations, we have high strength, reasonable amounts of strain hardening. And these materials are defect free. There are no other defects except the lattice defects that we have. So therefore, the realization of ultra high strength, good ductility, and dislocation based plasticity can be seen. And at the time, and still I think this is the best copper that is available in the market, which is really strong and reasonably ductile. So among the wide variety of processes that I just listed to make different nanostructured materials, high energy ball milling is the one that can offer you a good amount of advantages. Of course, there are some disadvantages that I would also be talking about those disadvantages and also the strategies to overcome these disadvantages. Give me a second, please. So in ball milling, what happens is that you will have a small container, and then in that you put balls and also powder particles of your interest, and then close it and subject to some kind of shaking. And as a result, these balls impinge or bombard your powder particles. So your powder particles get entrapped between two balls or between the container inner surface and the ball. So as a result, you transfer some kind of mechanical energy into the powder particles, and as a result, you improve the overall free energy of the powder particles. by nucleating several kind of lattice defects such as vacancies, dislocations, stacking faults, and so on. And the free energy becomes so high that in order to minimize and become stable, the internal structure gets rearranged by forming small nano grains. That's what is the mechanism of the nanostructure formation in ball milling process. And I'll come to this part later. That is the variation of mechanical properties based on the strain rate using nano indentation. This is a sample which was made using electrodeposition. This is a nanocrystalline nickel. As you change the increasing loading rate, you see a change in the behavior here. And yeah, I'll come back to this part later. So when we make materials using ball milling and then subsequently compact, they look like this. And this is about 1 centimeter in diameter and roughly slightly more than 1 centimeter in thickness. So we made these small discs, and making larger sample than this is difficult in this process. And we call them as bulk samples because when you compare the size of the sample to the microstructure length scale, see here, this is a dark field image obtained using TEM. This length is 200 nanometers. These white regions are grains, and that's when we measured the grain size using the statistical analysis. It shows that the average grain size is about 42 nanometers. And here you have a X-ray diffractograms that shows that you have a pure aluminum here. And when we look at the peak broadening analysis using X-ray line profiles, it shows that they are all nanocrystals, and the grain size that we have estimated using the Schreier equation from the X-ray line profile analysis closely matches the grain size that we have obtained from the TEM dark field image analysis. And the inset here is also a diffraction pattern that shows that it's a pure aluminum. And we published this work sometime in 2014 in Journal of Alloys and Compounds. And I mentioned before that your flow stress sigma is a function of epsilon, that is strain, epsilon dot strain rate, T is temperature, S is the microstructure. Different microstructural parameters are put together into S. So when you vary epsilon, or when you vary epsilon dot, or temperature, or microstructure, sigma gets influenced. So when you make a cumulative effect of all these things, it gets represented by this equation. And then M is a parameter which you call it as strain rate sensitivity. At a given strain, if you can vary epsilon dot, we'll see what sort of change can happen in sigma. And that M value tells you whether your given material is reasonably ductile or not. And the actuation volume mu star tells you, the magnitude tells you what sort of lattice defects have helped you in making these materials ductile. And this paper was also recognized as one of the excellent articles in industrial scientific research by an agency called Advances in Engineering based in Canada in 2014. And if you see the numbers here, we have the variation of M value from 0.024 to 0.054. These are reasonably good. That shows that you can make a acceptable levels of material with acceptable levels of ductility. As I mentioned before, not just the pure elements, we also wanted to make some kind of two-phase materials where the dispersions are also of the nano size. So as a result, we added some kind of lead to it. Both lead and aluminum lead are not miscible in liquid state as well as the solid state. And then we made a two-phase material where the average aluminum grain size is also made as 42 nanometers with respect to the presence of lead. And then when we compacted this powder processing at 300 degrees centigrade, we got a disc like this. The microstructure is like this. This is a bright field image. This is a corresponding dark field image. And this is the diffraction pattern. By indexing it, it shows that we have the presence of both aluminum and lead. And even after exposing to 300 degrees centigrade, you could retain the same two-phase structure. Here it's pure aluminum. When you add 1% lead, you see that you have the presence of lead peaks in X-ray diffractograms, and then with the increase in lead further up to 4 atom%, we have the increase in the intensity of the lead peaks as well. That shows that aluminum lead have remained as two different phases intact even after subjecting to high temperatures during spark plasticity. And this work and then the associated mechanics of plasticity, when we explain all those things, we published this in Metallurgical Materials Transactions in 2014. And then these are the microscopical details. We have a high resolution TEM here to understand the grain size of lead, particle size of lead, not the grain size. And also, this is a different kind of imaging technique where you see that there are some boundaries that shows some kind of white regions. And this technique is based on TEM. We call it a STEM, scanning transmission electron microscopic mode. And this is Z contrast imaging. That means the contrast varies based on the atomic number of these elements. For example, the bright regions are from lead and the dark regions are from aluminum. Aluminum atomic number is 13 and lead atomic number is about 72. So therefore, lead becomes brighter in this. This only tells us to understand about the locations of aluminum and lead that are sitting. So this is a large aluminum grain, large in the sense this is 50 nanometers. You can understand what I mean by large, and also you have a smaller lead particle sitting in it. So that makes a perfect scheme for the dispersion strengthening. And we have explained all these things based on the modified Oro-1 analysis, and also by incorporating the nanoscale mechanics into this. Okay, so I'm not going into this mechanics, the in detail research part of it, because that's not important for the FDP. But any of you have been interested, please ask me these questions later in the interaction session. So at a given grain size, lead is softer compared to aluminum, and also aluminum and lead, they both belong to the FCC structure. The other sequence that we have developed is the aluminum tungsten alloy, and this is the sample that we have here. And after ball milling, we have the presence of both aluminum and tungsten. But after sintering at 475 degrees centigrade, we see a precipitation of an intermetallic called Al12W. And then it shows that, and we published this work in Philosophical Magazine Letters. And these are the microstructural details from TEM. You have the presence of both aluminum and tungsten here. These are all the grain size and particle size statistics of aluminum and tungsten. And hardness is really high, more than 5 gigapascal in an aluminum-based system. And even the modulus is 145. That's really good. And for this paper, we also got some international prize from the James Clerk Maxwell Foundation, which is based in the UK. And still, this article is we published in 2014, and even after 8 years, this is one of the top 3 articles. It was 2 sometime back, but I think now it's at 3. Top 3 articles under most read articles in Philosophical Magazine Letters, and I'm very happy to inform that to you all. So now we have seen what happens when you add lead to aluminum and make it nanostructure. We also have seen what happens to aluminum when you add tungsten to it. But now if we add both tungsten and lead in little bit of quantities simultaneously, what happens? We did not get powders, but we got chunks like this, and then we still have a multi-phase structure, and it remained intact. And the best part here is that everything got compacted during milling itself, so you don't need to compact those powders using some high temperature or some external pressure. And that shows that this sample is kind of ductile. And further, whatever particles or chunks that we have seen here, we made them into discs like this. So that means these chunks can be made into nice discs and start using it in the final application wherever you want. But definitely for not large scale application, but small scale applications of millimeters or micron level. And we published this work in Philosophical Magazine in 2016. And see here, these are all different particles of lead and tungsten. And you see these atomic planes here. These are all the atomic planes. And you can also measure interplanar distance and interatomic distance using all these. This is the bright field image, and this is the corresponding dark field image. This is the diffraction pattern, and the high resolution imaging. So this is 5 nanometers here. And based on this, you can understand what would be the grain size of this particle, because this is the grain boundary. When you try to bring this into focus, this went out of focus because of the misorientation. And further, you see small particles here which are faceted in nature. They are faceted particles. So, and also when we try to understand the variation of hardness and strain rate, there is a strong dependence of hardness. That means when you vary the strain rate, hardness also increases. Hardness and flow stress are directly related in a sense using some kind of constraint factor proposed by the scientist called Taber, that is Vickers hardness by 3 roughly gives you the yield strength and flow stress of your material. And in this, compared to your aluminum lead and aluminum tungsten, the M value is way higher, 0.07. That shows that when we have multiple phases in a given material which are of different nature, one is FCC, the other is BCC, you have a very high and positive strain rate sensitivity and also low activation volume. And so, in summary, you have aluminum here in terms of strain rate sensitivity, and when you added lead here, it increases. When you added tungsten, it comes down. When you added both lead and tungsten, it really goes up. And the activation volume for conventional metals is 1000 B cube, where dislocation, forest dislocation plays a major role in governing the mechanics of plasticity. But here you see that it's always below 10 B cube. B is the Birch's vector. And that shows that the grain boundaries and other latitudes play a major role in nanostructured materials to govern the mechanics of plasticity. And we also mentioned all these details in some encyclopedia article that we published in 2016. So mechanics of plasticity in two-phase systems at nanoscale are complex. They are not straightforward, and there is an interplay between the critical grain size versus the second phase. And there is an experimental evidence that we have shown that strain rate sensitivity of two-phase bulk nanocrystalline materials is really different based on the nature of the second phase. And for conventional materials, SRS is an order of magnitude higher compared to coarse grain materials. And the contribution to high strain rate sensitivity comes from the small grain size, also second phase, and its crystal structure. Sometimes the synergistic effects based on lead and tungsten. And if you can make, and now this work shows an optimism to make nanocrystal materials ductile enough with the incorporation of multiple phases with nano-sized microstructural features. But making these samples with the above set features and distribution is not an easy or trivial task in different alloy systems of engineering importance. You definitely need a careful microstructural engineering. Okay, the other part is on high entropy alloys. So how much time do I have in this session, Dr. Srinivas Prasad?
Sir, actually, 10 minutes break can maybe
okay,
taken, and we can continue, sir.
Okay, then we'll break here because this is a different topic again.
Okay, sure, sir.
Rather than stopping after starting it, we'll stop here and then after the break I will start.
Sure, sir. Whenever you are ready, you can continue.
Okay, now it is 7:58. Then exactly
Yes,
at 8:08 we will start, or 8:10.
8:10 we can start, sir. Sure,
8:10 we will start.
Sure, sir.
So I just want to talk to the remaining audience. Am I audible clearly to all of you?
Yes, sir.
Yes, sir.
Are
Yes,
you
sir.
all,
Yes,
are you
sir.
all there, or are you busy with your respective work? You're all paying attention to me, right?
Yes, sir. We
Yes,
are
sir. Yes, sir.
Thank you. Thank you. Yeah, we will meet at 8:10.
Okay, sir. Sir, I would like to welcome you again, sir, for this part 2 of session 1, first day session.
Okay, I'll continue.
Sure, sir. Thank you.
Thank you. Yeah, thank you all. The second part is on the novel set of materials. Here, till now, maybe until 2004 or so, we only know that, for example, if you have aluminum alloys, aluminum is the dominant material. Steels, iron is the dominant material. And super alloys, nickel is the dominant material. Likewise, you have a dominant material, and in that you added some alloying elements and then made the material of your interest for a given specific application. But a radical concept that has emerged in the mid 2000 is that when we add all the alloying elements in equal proportion, what sort of microstructure would develop and what sort of properties would come out of it. So those materials where you have no bias towards any material with respect to composition are called as high entropy alloys. These are also called as multi-principal element alloys or multi-component alloys or complex concentrated alloys. And we also made these alloys into nanostructure and then observed the properties. That's why these materials are also of relevance to you with respect to the current FDP. Normally, you see this Gibbs free energy equation delta G equal to delta H minus T delta S. For a given material to become stable, the delta should be as negative as possible. And for that, there are different strategies, whether you make delta H negative or make delta S positive. The conventional way of developing materials is making delta H negative, and that has reached its limit. And now the strategy is to make delta S more positive so that this whole term becomes more negative, contributing to the more negativity of delta G. And delta S mixes follows some kind of Boltzmann's equation given by here. That shows that if you have more number of elements with different compositions, then your delta S increases. Delta S is the entropy term. And at atomic scale, when you have different atoms, like each color represents one element here. This is 1, 2, 3, 4, 5, and they get mixed like this. You form a solid solution like this. That is the mixing of atoms at atomic scale forming a new alloy. And these are called as high entropy alloys. And the mixing entropy associated with the formation of this structure is believed to give the stability to the structure. And these are all different properties that people have seen in these high entropy alloys, where you could see that whatever properties that were observed in these new materials are for the first time, which were not exhibited by the other materials. For example, you have aluminum alloys, fiber reinforced composites, magnesium alloys, nickel alloys, steel and all here, but your high entropy alloys are shown here with respect to yield strength and hardness. Professor Michael Ashby of the Cambridge University, I request you all to mute, please. Professor Michael Ashby of the Cambridge University, he made several plots between different properties so that they could help you in designing different materials or systems, material systems for a wide variety of engineering applications. And when you keep the data points that you realize out of these entropy alloys, they are way above or in the region where the other materials are not occupied so far. And the four possible effects that come out of these cocktails are the mixing at atomic scale is that a entropy effect because of the disorder that they bring at atomic scale, and sluggish diffusion. To form any new material, diffusion is very important, which is a mass transport at atomic scale. And because of the presence of the wide variety of materials whose melting points are different, whose densities are different, whose diffusivities are different, either room temperatures, high temperatures, you expect that you form some kind of an amorphous structure, but that's not the case. And also because of the variation of the atomic radii of the participating elements, you also expect some kind of distortion in the whole lattice, contributing to the high hardness. For that, the original attributes of different elements, you put them together, they also get intermixed, and you bring some kind of a cumulative effect, which is called as a cocktail effect. But later on, when these were proposed way back in 2008 or so, but now it's 14 years later in 2022, most of the things are not really are kind of possible. For example, sluggish diffusion. When you say that, when you expect that diffusion is slow here in this, diffusion of what? For example, there is no solute, there is no solvent here. Everything is the same proportion. You never know what is diffusing and how it is diffusing. As a result, diffusion is not really slow when it was actually measured. High entropy effect is there, and lattice distortion is also affecting the properties. Cocktail effect is something again that has to be seen experimentally. And these materials again, the example that I'm showing here is aluminum, cobalt, chromium, copper, iron, nickel, and all are taken in equal proportions. Therefore, you cannot call this as an aluminum alloy, you cannot call this a cobalt alloy, you cannot call this a chromium alloy, you cannot call this as a copper, iron, or nickel alloys, because all are in equal proportion. That's why you just call them as multi-principal element alloys. In comparison to one principal element that exists in conventional materials, which are diluted alloys or diluted composites, here in these concentrated systems, you have the presence of all the elements in equal proportion. Therefore, you cannot give a name to it. and we made them using ball milling and then compacted them using different wide variety of techniques. And these are different physical properties. See here, initially you see the presence of these are X-ray diffractograms. You see the presence of all the participating elements. With the increase in milling time up to 60 hours, you see that you form a single phase FCC structure, which is really good. So all the elements went into one lattice and formed one, I would say, a host lattice, I would call that as it is. And then we try to track the formation of the structure here, solid solution formation, using the measurements of D spacing, that is interplanar spacing, with respect to the milling duration. We figured out where exactly the solid solution forms and where exactly the saturation happens. And we also measure the variation in the lattice parameter and variation in the atomic diameter, how they help, how they affect, and so on. Coming to the powder morphology, you see some kind of plates here after ball milling. Nice plates. You see, this is an unusual structure. And the grain size is really small, about 10 nanometers. The average grain is 10 nanometers. And you have the presence of a single phase structure, although there are several elements. And when we try to measure the interplanar spacing, that corresponds to the one that we measure using the X-ray line profile analysis. And to understand the mechanical properties of these materials, we have to compact them into bulk discs. We did that using spark mass sintering using the facility in ARCI, Hyderabad, and these are the samples. You see such a nice sample. We cut them for further calculations. So such a bulk sample we have. And after spark process sintering, interestingly, you see a phase transformation. You saw a new phase that is an ordered BCC structure in addition to the parent FCC structure. So eventually you develop a two-phase structure, which is something that you want for all engineering applications. And that two-phase morphology can be seen in the SCM micrographs. And this is the chemical analysis that was done using the energy dispersive spectroscopy. So this is the nominal composition of all the elements, and you have a dark phase, black one here, and a white phase. And the white phase is higher in copper content. And these are the transmission electron microscopic images of this two-phase system. And you have a two-phase presence that we could see from the electron diffraction pattern. And the grain size is also increased, say from 10 nanometers in the mill condition to 112 nanometers. And also there are some larger grains which are about more than 1.5 microns. You see here large grains and also small grains here. We have twins, so many microstructural parameters. The microstructure is really, really complex. And these are the twins. We used high resolution transmission electron microscopy to understand this twin behavior. See here, we did not do anything to it. These twins have formed during heating. This is 5 nanometers. They're all atomic planes. They're all atomic planes. And then when we measure the hardness of the samples at different illumination loads, we got about 6.4 gigapascals, and this is the best hardness that anyone could report, anyone have ever reported in this LI system. And then we also try to understand the strain rate sensitive behavior of this new nano structure high entropy alloys, and it shows that the strain rate sensitivity is much low in these alloys compared to the conventional dilute alloys. And also the activation volume is also much low. And when we try to understand the origin of the hardness of 6.5 gigapascals in the systems, we figured out that strain hardening, lattice frictional stress, Hall pitch strengthening, solid solution strengthening, and also twin boundary strengthening are responsible for the high strength that you have seen. These are different calculations that we have performed, so I will not be discussing those details. Hall pitch strengthening, solid solution strengthening, and also I have discussed this figure in the beginning of this lecture, that at different grain size regimes you have different Hall pitch constants, and you need to consider those. And here twin boundaries also govern the mechanics of plasticity in a way the grain boundaries influence. Therefore, Hall pitch type of dependence, that is 1 over root D, is also assumed here for the twin boundary strengthening as well, and it works very well. And the overall strengthening is about 2.3 gigapascals. And when you look at the Taber's constant factor, it turns out to be 2.7, which is well agreement. And in summary, we have started with different elements in powder form. Here, the different size shows that different atomic diameter. We mill them together, and this is the grain particle morphology. We made a big disc out of it using spark loss sintering, and we indented this using micro indentation and nano indentation. We have evaluated different strengthening parameters, strengthening mechanisms that are responsible for the high hardness to and we have published this paper in Active Material in 2017, and this is a very prestigious journal. So the standard sensitivity value is of 0.0084. That's very low. That means these materials are not strain sensitive at this microstructural features. And the activation volume is about 13 BQ. B is the Burgess vector. That's also pretty low. And this we have discussed before. Again, you have a multi-phase structure here. FCC plus B2, and it's nanostructural feature, microstructural features, but the SRS and the activation volume follow the formulations that were exhibited by the simple nanocrystalline materials that we have seen before. A combination of energy ball milling and spark process sintering have been utilized to fabricate an ultra-fine grain. If the grain size, the average grain size is less than 100 nanometers, you call it as nanostructural material. If the grain size is above 100 nanometers and below 1 micron, that is 1000 nanometers, you call that as ultra-fine grain materials. Above 1000 nanometers, which is 1 micron, you call them as microcrystalline materials. And structural and microstructural investigations reveal the presence of solid solutions, bimodal grain structures, quins, and so on. Comprehensive analysis of strengthening mechanisms was done, and a very low strain rate sensitivity we have observed with a kind of low activation volume. And interfaces such as grain boundaries, twin boundaries, and phase boundaries play a key role in dictating the deformation kinetics of this high entropy alloy. And that is one. My other continuation will be on this. That is one system: aluminum, cobalt, chromium, copper, iron, nickel. There are other systems that we have developed recently that include the background like this. The nickel-based superalloys are reaching their limit. For example, now the turbine engines, whether you use them for the airborne applications in your flights or any other aerospace applications, or land-based applications for power generation, they're reaching their limit. That means you need to, in terms of efficiency. So in order to improve the efficiency, the only way that you can have is improve the operating temperature levels. When you want to increase the operating temperature levels, you need to find a different set of new materials. And the only way is to look at a strategy where you can develop altogether a new material which can replace the existing nickel-based superalloys. So nickel-based superalloys operate around 800 C, and you need to operate above 1000 C in order to have a better efficiency. And these nickel-based superalloys also melt at 1239 degrees centigrade. So you need to develop new materials with melting points more than 2000 C, and the whole driving force behind this exercise is that to find applications of next generation gas turbine applications.
Excuse me, sir.
Yes, please.
We are not able to see the new PPT.
Now?
Yes, sir.
Yes, sir, it is visible.
Okay. So nickel-based superalloys are operating the ones which are in use for gas turbine applications. Either they are of airborne applications in flights and the space applications, or land-based applications for power plants and so on. But now, in order to improve the efficiency of these turbine engines, you need to increase the operating temperatures. In order to increase operating temperatures, the turbine engines have to be made of a different set of materials whose melting points are high. So as a result, nickel-based superalloys have to be replaced with a new set of materials. So when you look at the molybdenum, niobium, tantalum, tungsten, and these are called as the refractory elements individually, and we want to develop a new alloy system by taking these elements, molybdenum, niobium, tantalum, tungsten, equiatomic proportion, equal proportion, and these are concentrated alloys. And also we want to vary the microstructure length scale to make it nanostructure, so that you derive the incremental sense of strength from the high pitch takeout dependence, and we develop our own materials in the lab and testing. And also, when you look at this material, it was also developed and published this work by US Air Force Lab. But the problem is that this is extremely dense. And before even you qualify this, of course, it has to go through several types of evaluations with respect to oxidation resistance, and then high temperature strength, ductility, and all that, high temperature corrosion, and all that. Keeping that aside for the time being, even if you look at the density part, this is extremely dense. Therefore, now to reduce the density, we added titanium, which is also some kind of high melting point but less dense. Because steel density is about 7 grams per cc, and aluminum is about 2.7 grams per cc. And this titanium also offers density of only about 4.5 grams per cc, and also a relatively high melting point, which is about 600 degrees centigrade. And based on the outcome of this work, we also developed the other alloys I'll be talking to you in a few minutes. So initially, when we took all these elements in equiatomic proportion, you see the texture diffractogram shows the presence of all the elements. After 30 hours of ball milling, you see a single phase BC structure formation. And when we subjected these powders to spark velocity at elevated temperatures, we see the formation of different phases. And this is the microstructure, which shows 3 different phases, 1 PCC and 2 FCCs. And you see the particle here, either bright or dark particle, which is less than 1 micrometers. This is 2 micrometers. So the characteristic length scale is less than a micron.
Excuse me, sir.
Yes, please.
I have a small question on this.
Yes, please.
While developing this high dense material, is there any specific chemical composition of each individual element?
We are making it equal at the moment.
Okay, so all the elements
Are equal in proportion.
Okay, so can we have some glimpse of the synthesis?
It's ball milling again.
Ball milling.
Ball milling. I mentioned that in my previous presentation. How we do ball milling, how the nanostructure formation happens in ball milling and all.
Yes, sir. Got it, sir.
So to understand the relative fractions of these phases, we did the BSc SCM analysis that shows that BCC phase accounts for about 47%, and the first FCC phase accounts for 16%, and the FCC accounts for 36%. So it's really a multi-phase structure, which is good. And when we try to understand the relative compositions, just now you asked me this question. Initially, we started with the equal participation from all the elements: molybdenum, tantalum, titanium, tungsten, 20, 20, 20, 20. Okay. And then after we made the bulk sample, the compositions have varied. And the gray phase has got a composition like this, and dark phase has a composition like this, and a bright phase composition like this. We have all the participating elements, but iron is something that we have not added, but it came from the milling media, and that's also good for us.
That is as a foreign material, sir?
Yeah, that we did not add it intentionally, but it came from the milling media as a contamination. This is the disadvantage of a ball mill.
Okay, sir.
Contamination. But now, when you look at the hardness variation with load, you got hardness as high as about 18 gigapascals, which is extremely high, and it got saturated around 13 to 14 gigapascals. This is the saturation limit you can see. And you have exceptionally high hardness, and this variation of or the decrease in hardness with increase in injection load is called as the indentation size effect. And when we try to understand the hardness by density for our material versus the several materials that are reported in the literature, our value is exceedingly high because of the presence of titanium, and also the nanostructure that was there in the material. So we have got remarkably high density normalized hardness in this system compared to the rest of the family, rest of the alloys in this family here. And we published this work last year in Materials Science and Engineering. And again, like the way we have done for the other systems, which is aluminum, cobalt, chromium, copper, iron, and nickel, in this also we figured out that several mechanisms involving lattice frictional stress, strain hardening, Hall pitch strengthening, solid solution strengthening, coming from various phases of this material, when we assume them to be operating as independent as well as any two contributions, it works very well. And out of that, solid solution strengthening, which is here in brown color, and Hall pitch strengthening, which is there here in orange color, account for the larger fraction of the overall strength. And to understand why the load has decreased, why the hardness has decreased in the indentation, this is how your indentation is made, and we have this is the image after making the hardness measurement. This is schematic and what exactly happens in different phases with respect to dislocation interaction between the tip and also the material. And this is a chemically homogeneous material because all the phases have got all the elements, but plastically non-homogeneous in the sense that you have one BCC phase and two FCC phases. The plastic deformation in FCC phase is really good, but PCC phase is not that easily deformable. Plus, it also exerts back stress on the FCC phases. So that brings the overall plastic non-homogeneity in the system. And the analysis shown by the two scientists, William Nix and Eugene Gav, when we adapted them, it works really well to understand the indentation size effect. These are all different indents that are made. This is 150 micrometers. This is the H0 that shows that you can get as high hardness as about 11.8 gigapascals, which will not get affected by the load that you apply. And H star means up to about 1 micron or so, you have this effect, but beyond that, when you indent beyond that, it gets saturated. And you also need the geometrical need dislocations, which are not there in the beginning to account for the plastic deformation at low loads. As a result, you have the high hardness. You need about 6.9 to 10 per 15 per meter square of dislocation density to account for the initial hardness that is observed. And to understand the variation, the influence of titanium, because we have just seen that titanium has done really wonders. It gave us the extremely high hardness and extremely high density normalized hardness. Then we wanted to see, this work is in review now. We have made two systems. One is binary, that is molybdenum 50-50, and ternary molybdenum titanium 33, 33, and 33. So this is the sample we made using vacuum arc melting, and then we also homogenized these samples at 1400 degrees centigrade for about a day. And irrespective of that, what we have seen is that a single phase BCC structure that was formed after arc melting has remained stable even after exposing these materials to very high temperatures for longer durations. And titanium, which is of different crystal structure compared to moly and niobium, also did not make any difference. It's same PCC. And interestingly, this is the microstructure with moly and niobium, and this is one with titanium. You see that the grain size has decreased. So titanium acted as a grain refiner, resulting in the grain refinement. And when we heat treated the samples, you see that the grains have got some kind of skewed morphology, but the average grain size remained intact. When we try to understand the hardness versus load, we have got reasonably high hardness for the microstructure length scale that is there in these materials. Plus, when we compared our data with the other systems of the same family, that shows that you really don't need so many elements need to proportion, but with just binaries and ternaries, that would do your job. And solid solution strengthening appears to be a dominant mechanism in these materials. And further, the density normalized hardness also shows that you have very good numbers for binaries and ternaries compared to quinary, quaternary, hexanary systems. And the other part is the oxidation resistance is also important. So tantalum is offers very good oxide layer. when you expose these materials eventually to high temperatures. With that intention in mind, we also developed molytantalum and molytantalum titanium. So here you see that you have a multi-phase structure. These are X-ray refractographs, and we published this work a few months ago in Materials Let's. And these are the SEM micrographs. Again, your microstructure length scale is submicron, multi-phase structure. And then hardness is also extremely high, 16 megapascal in just binaries and ternaries that you have not seen even in quaternary and quinary systems. And this variation of hardness with load, which is the indentation size effect, a very pronounced one that you have seen in this case also, is explained using the geometrical linear dislocations to account for the very high hardness in the beginning of your hardness measurement at low loads. And influence of iron and titanium is not required for this session. So let me go to the other one. So this is the new composition. You see how many elements here? Aluminum, cobalt is not there. Aluminum, chromium, iron, molybdenum is totally 6. It's totally 6. So we started with the elemental powders. You see here in the beginning of the milling, we have the presence of all the peaks of all the elements. But as you increase the milling up to 60 hours, you formed a two-phase structure, an FCC and a BCC. BCC is a dominant phase and FCC is the minor phase. And the transmission electron and the other studies shows that we have a two-phase structure clearly coming from BCC and FCC, and the grain size is about 9 nanometers. It's extremely fine, extremely fine. And now, when we subject these smaller grain size materials to high temperatures, there is a grain refinement. I think that's taking the total advantage out of the nanostructure. So in order to preserve that, what we have done is that first thing is to understand the microstructure using high resolution TEM. It shows that we have the presence of both the phases of grains, which are very small in size. This is 5 nanometers. You can understand the size of these grains. Then the circles here, the red ones correspond to BCC, green ones correspond to FCC. And then there is a different technique called high pressure torsion. Normally, high pressure torsion means you apply very high loads at very high strain rates so that the microstructure gets refined. And this is one way of making a nanostructured material from coarse grained materials. But here in this case, we did not use it for the structural refinement. Instead, we use this technique to compact the powders into the bulk components so that you can measure the mechanical properties. At the same time, the whole process operates only at room temperature. You will not see any grain growth. So even after high pressure torsion, you see the same kind of structure that we have seen. The structure that we have seen after ball milling has remained intact. And these are the two phases after HPT, and two different colors shows that here red is BCC, green is FCC, and both are shown together here. This is the second backscatter image under SEM, and these are the different compositions that we have obtained from two different phases. After HPT also you have the same kind of structure, but the only thing is that there is a grain size distribution. You could see two maxima. Initially after ball milling, we have seen only one maximum with an average of 9 nanometers, but now you have two maxima, one at 8 nanometers, other at 12 nanometers, which is good. And also the high resolution TM analysis is also consistent with what we have observed using XRD and SEMs. And the hardness shows that you have very high hardness at the center, very high hardness at the edge and somewhat lower at the center, and that comes from the strain variation that you apply during this torsion. And also when we measure the hardness at different indentation loads, in this case it doesn't show any indentation size effect. That is, the decrement of hardness with increase in load that we have seen in other systems is not seen in this system. There is a reason for it. And also the Hall patch constant that we evaluated to understand what exactly is happening, we see that its Hall patch constant is very low, and that accounts for the grain size softening. That is, you have grains about 8 nanometers and 12 nanometers, which is close to 10 nanometers. I kept on telling in the beginning that if the grain size falls around 10 nanometers, your grain boundaries become weak under the application of load, and as a result, things like grain boundary sliding, grain rotation, and coalescence, are grain boundaries acting as sources or sinks of lattice defects like dislocations or stacking faults or partial dislocations would come into picture, and that would result in enormous Hall pitch effect, and that we have seen experimentally in the system. And this is the whole schematic. You have BCC grains and FCC grains, which are extremely fine, 10 nanometers. And when you look at the atomic structure of a grain boundary, these atoms are different nature. Here you have shown here. One is BCC, one is FCC and BCC, but the grain boundary will not show any crystal structure. And the atomic shuffling that will happen in the grain boundaries is the major reason for the softening that you have seen in the systems. To summarize, so concentrated alloys offer near infinitesimal computational space that have not been explored till now by the scientific community, and these materials already started to show unprecedented mechanical properties that were not observed in other materials. And also you need to apply your mind very carefully and also judiciously while selecting materials and their compositions to make materials for a better tomorrow. And since you are making a lot of materials with very concentrated proportion, sometimes recycling is also important to get the materials back and then reuse them. And as I said, this work is in progress, and we still have to submit this work to journals, which we will submit, I think, in a week's time. And this is our building, very new one, where we already moved in. We are working from here, and the work that I presented here from many people who have already graduated and working at different places. But currently, Dikshit and Madhu are with me, and they are about to finish their PhDs. And the collaboration from ARCA with Dr. Sudarshan Fani, Anjali, and Sai Karthik is acknowledged here. And the several scientific discussions that we hold with Professor K. Banashikar Rao, who was with us as a dean as well as a Pratt and Whitney chair for a long time, and who is at IIT Hyderabad now. We discussed several things with him, and then also Dr. Narayana Murthy from ISRO, who will be performing as, who will be collaborating with us on high temperature compression testing of these materials before we qualify them for the turbine applications. And also the collaboration with Dr. Yulia Ivanishenko of Karlsruhe Institute of Technology in Germany is gratefully acknowledged. And the funding for all this work has come from Institution of Eminence program granted to the University of Hyderabad, DST PERS, DST FIST for the support of the equipment. We sincerely acknowledge all those supports. And this is the main gate of our university at the entrance. And with that, I thank you all. And if you have any questions or any concerns or any discussion, I would be happy to discuss with you all.
I have a small question. Hello.
Give me a second. Yeah, please.
You are talking about the grain size. Anything that is less than 10 nanometers, it will not give good results. So that means what is the ideal size that we can use for any nanometer?
About 20 nanometers.
So the ideal grain size is 20 nanometers.
It's not ideal. I won't call it as ideal. About 20 nanometers, at least 10 is positive. But once it goes to 10 nanometers, you have all sorts of effects.
Is it applicable to any application or depends upon?
Ideally, you want a stronger material, right?
Yeah.
Yeah. So for most of the structural engineering applications where strength is important, better to have materials with the grain size 20 nanometers and above.
Oh.
Any other questions from anyone?
So normally we see that the hardness of the materials are being enhanced by doing all these processes most of the time. So is there a way of increasing the fatigue strength and this all this
Yeah.
kind of properties?
For better fatigue strength, all you need is a fairly smaller grain size,
Right.
so that the crack initiation gets delayed, even if it gets delayed, or even if it gets nucleated because of the small grains, the dislocations will blunt the crack and stopping the crack growth. Therefore, fine grain structured materials are important for fitting applications. So once you have a fine grain structure, you also have a better hardness.
Yes. But normally we see that hardness and fatigue strength are somewhat inversely proportional. So if
Not
the hardness
always. Not always. Not always. It depends on the microstructure and also constituents of the microstructure.
right.
Again, it depends on whether you have a single phase material or two phase material. If it is a single phase material, your fine grain size directly affects your fatigue strength in a positive way. But the moment you have inclusions, those inclusions act as stress risers. Cracks nucleate at that point. So then your grain size has got a minimal role in telling what sort of fatigue strength you have got.
Yes. So request all the participants, if you have any questions, please raise to our sir.
Is it possible to see you all? I just want to see who are all the participants here. Is it possible?
Request the participants to please turn on your camera. Participants, turn on their camera so that we can see you all at a glance. So participants, if you have any questions, you can please raise so that we'll have some more interaction.
We can keep
So
discussing.
this last half an hour is for interaction only, so that knowledge enhancement is done in this area. So most of the time research is at the present is going in respect to materials, enhancing the properties of materials, both in mechanical engineering and materials engineering.
So what I presented is at the intersection of mechanical materials.
Right.
And most of this work was done by mechanical engineers. Let me admit this to you. Their BTech was in mechanical. Those who executed this work, they're all BTechs in mechanical.
Right. If there are no more questions, I think we could wind up this, sir. So I would like to thank you, sir. Thank you.
Somebody is.
Yes, Mr. G. Veeraya. Raising any question?
Yes, sir.
Yeah, please go on.
You have mentioned unit for hardness is sometimes GPA, and in one slide I have seen that is in terms of Newton meter per.
Yeah, in SI units, you can always put it in either megapascal or gigapascals. But the one that you're referring is when we normalize the hardness with the density. So megapascal over again grams per cc or kg per meter cube, when you put it, that it gets into a different form. Because for airborne applications, density is also important. You cannot have a very dense material, although it is strong enough for airborne applications, especially in the aviation sector. So their density is also important. So hardness over density is a critical parameter for those applications.
Sir, what the GPA indicates, sir?
Gigapascals. If the
Gigapascal
hardness
only, giganewton per meter square.
Yeah, giganewton per meter square. We convert them into SI units. We convert them into SI units. Nothing great in that.
Okay, sir.
Your voice is
Hello?
breaking. Your voice is breaking. It's not clear.
Hello.
Yeah, please tell me. I can hear you now.
Sir, that meter square indicates nothing but area of indentation only.
Yeah. Right. And Newton is load up that you apply. Normally you apply in grams or kgs and you convert into newtons.
Okay.
1
Okay, sir. Thank
kg,
you.
1 kg force equal to 9.8 newtons.
Yes, sir. Thank you, sir.
And also indentation dimensions will be either millimeters or micrometers based on the load you apply and also the relative hardness of your material. That you convert into meter square so that everything is uniform.
Okay, sir. But generally, I think we are not going to represent hardness in terms of units, right? You only hardness number on.
Scientifically, we should. The number works only in industries, but in scientific work, you should have the units. Otherwise, suppose if you are measuring the tensile properties, how will you compare your hardness with tensile properties?
Okay.
Tensile properties strength you get in either MP or GPA.
Yes, sir.
Yeah.
What is the role of indentation material? Is it a change from one material to another material?
It should be hard enough. Normally we use diamond.
Yeah.
So it will not have any effect on the material unless and until your working material is stronger, then it deforms the diamond. That's it. Your machine is gone. Buy a new diamond.
So it should be more hard than the material we are working.
Yeah, it should be harder than the one that you are indenting.
So diamond is obvious.
If you can develop better than diamond, yes, you will replace it with that.
Okay.
So how can we correlate the strength and hardness? Generally, for example, if you say that I think it is GPA.
Yeah.
That means if hardness is high, then how can you say strength is also high?
Yeah, it is right. What stops you in thinking that? Let me pose a question back to you. It is well proven fact that you take any existing materials, you take 10 materials like one stainless steel, one aluminum alloy, one nickel based super alloy, and use Reco's indentation and measure the hardness and also make tensile samples out of those and measure the yield strength. Hardness by 3 just becomes equal to your yield strength. It may not be 3, sometimes 2.9, sometimes 3.1. It's in and around 3. It roughly gives you the strength, and they are directly related. If metal is harder, strength is also high. There is no doubt about it. Assuming that all other parameters are constant, the temperature, pressure, and everything that you are using for the measurement of hardness, you also maintain the same thing while doing the tensile test.
Okay, sir. Sir, and is there any relation between this hardness value and grain size?
Yeah, that's what I mentioned. Hall-Petch equation. Hardness and strength, as I mentioned, hardness and flow stress are related by a factor 3. So sigma y equal to sigma naught plus k into d power minus of I mentioned, right? Likewise, hardness equal to h naught plus h naught plus k into d power minus of. That k value will differ to a different number, but because of its nature, nothing is going to make a lot of difference. You still are going to have the same kind of dependence on the grain size. Hardness is proportional to 1 over root d. Like hardness is proportional to 1 over, yield strength is proportional to 1 over root d. Hardness is also proportional to 1 over root d. Only proportionality constant varies some magnitude. That's it.
Okay, sir. Thank you, sir.
Any other questions from anyone?
I think that's it, maybe, sir. Thank you, sir. Thank you very much for extending your expertise in this late hours, actually, to enlightening the participants with respect to this FDB on mechanical response of multi-phase nanostructured conventional and high entropy alloys. So it's an advanced area, and I think most of the participants who are very much into the research work can get benefited by attending this session. And all the participants, I think though they are not posing any question, they have imbibed this knowledge, whatever you have disposed today. Thank you very much, sir. And all the participants are requested again to join for the sessions in a similar way again tomorrow evening at 7 p.m. So for a few more wonderful sessions. And I request all the participants to be prompt in attending the sessions and by maintaining the time sharply at 7 p.m. because the attendance is also mandatory for this FDP, Atal FDP sessions to get the certification. That's the information I want to pass again with respect to the attendance part. Thank you very much, sir.
Thank you very much. Before you close, I just opened the chat box, and there is one with name Simhadur Raju posed a question here that what about the role of lattice defects in the case of polymer composites? So here the lattice defects, as long as it is crystalline material, the same kind of lattice defects are there because polymers either crystalline or amorphous. Sometimes they are partly crystalline. So if they are amorphous, there is no question of lattice defect. Forget about it. There is a different mechanism that happens based on the shear zone. Small pockets will act as we call them as shear bands. And there is a different mechanism that influences the mechanical behavior in polymers. Whereas if you have a crystalline part, then crystalline part acts as a second phase.
So that means the mechanism of plastic deformation is completely different.
Different if they are amorphous, totally amorphous. If it is crystalline, the same kind of analogy that we presented here are also applicable for polymers.
Okay.
If it is a mixture of crystalline and amorphous, then one acts as one phase, another acts as a different phase. The interface plays a major role.
Okay. That means between the layers.
Yes. Between crystalline and non-crystalline regions, or crystalline and amorphous regions.
Yes.
Hello, sir.
Yes, please.
Sir, for characterization purpose, is there any facility available at your end in HCU?
What
like
exactly?
XRD?
Yeah, you can use that.
Okay, sir.
So because I can also got some kind of widely accepted material and presented the FTP here, but that's not my intention. Whatever we have done here, we want to show you so that you will also develop your research culture in respect to academic units. That was the purpose I have taken. I hope at least some of you will do that. So once you also do the active research along with teaching, lot of topics gets refined, and you also can inspire several people, and your way of teaching also changes. This is my request to you all. I know you have your own problems in colleges and all. Administration won't support you with respect to infrastructure and all, but you put your efforts as much as you can. This is my request to you. And once in a while, you can approach our places and make use of our facilities.
So that is a good opportunity to our participants actually.
So I gave the email address there, so you can write to me whenever you need some facility. If it is available with us, we'll definitely extend our facility to you.
So all the participants are requested to make use of this wonderful opportunity provided by our professors, Koteshwara garu. Thank you, sir. I think.
Thank you very much.
If there are no more questions, we can wind off. Thank you, sir.